Yeah, hi, good evening, everyone. So, welcome to the open session for week 5. And I know that this week you have quiz also, so I'm not sure you have already watched the videos or not. So, any query before starting the session, week 5? If you have any query, anyone?
So,
Yes.
but is there any revision sessions for
Yeah,
quiz?
so that tomorrow session, I think for all both TA session is actually revision session this week, as well as the Friday session. That is not live coding session this time. It will be a revision session. Okay. Yeah. And also just look the all TA PYQ session where the PA have the TA have already discussed this previous year question every week wise. So that will also be helpful. Okay. If you missed that previous week, then you can see the recording also, or join all these come in this big TA session as well as the Friday instructor session. Okay, any other query from previous week? Anything? Okay, then shall I start the week 5 content? Okay, so let me share my screen. So, how many of you have watched the video content? If you have any query specific to week 5, if you have already seen the content. Okay, so let me start from the first topic, and then we will discuss. And in between, you can stop me and ask the query. Okay. So let me share the PDF for this week. Second. Yeah. Yeah, I hope my screen is visible. That week 5 content. Can anyone confirm?
Yes, sir.
Okay. Okay, so week 5 is basically continuous topics of the graph, and this weeks we are learning some advanced algorithms related to the graph algorithms, some applications related. Okay, so previous week you have already seen this traversal algorithms, topological sort algorithms. Now this week we will just play around the weighted graph. So what is this weighted graph means, and what are the possible application on the weighted graph? So first things, how the weighted graph we can represent in the program or in the mem data structure in the program or in the Python basically. Okay, so these are the main topics of this week. First things, we will discuss the weighted graph, and after that, we will discuss one topic, shortest path. Okay, and this is a very nice application. This is very common use application, and how we can find out the shortest path in the graph. And we have three algorithms here. One is Dijkstra algorithm, another is Bellman-Ford algorithm, and another is Flood-Warshall algorithm for this purpose. Another topic we have this week is spanning tree. Okay, and what is spanning tree? And generally we use the minimum spanning tree, so that we will also discuss. And what are the algorithms related to this spanning tree? So we have two algorithms, Prim's algorithm and Kruskal algorithms for this. So these are the main topics of this week 5, and based on the graph. So first things, weighted graph. So previous week you have already done, and in that week we only used undirected graph. We also use the directed graph in topological sort, but we not use the weight on the edges. Okay, and we only use the unweighted graph. Now this week we will discuss this weighted graph. So weighted graph means if your graph contains some value or weight on the edges. Okay, so that graph is called as a weighted graph. So it may be a directed or it may be undirected. Okay, so it could be a both type of graph, weighted graph. So here, let me just show you one. Okay, so there is no image. Okay, why this image is not there? Let me open the site. Okay, so no image is there. Okay, fine. Yeah. So first thing, weighted directed graph. So how this is the representation, how we represent this in the program. So graph is look like this. So weighted directed graph means suppose we have vertex like this. So B, C, and D, and this way that vertex will be connected like this. So and like this, okay, like this directed edge, and after that all each edge will also contain some value. Okay, so like 10, 5, 4, 3, 6, like this. Okay, so each edge have some weight. Okay, so this is called as a weighted directed graph. So now how we represented this? So first things, now this time for each edge we will also contain the weight value. You can see now we have to represent one edge, we have the starting source vertex. If this graph is a directed graph, so that means first value in the tuple is representing the source vertex, and second value is representing a destination vertex. So that means AB for this graph I am writing here. Okay, so AB, and what is the value for this edge? So this is 10. So like this, we can represent each edge like this. So that means A is this is the edge is going from A to B, and edge contains the weight 10. Okay, so this is the representation for edge in the weighted directed graph. So now you can see D edges. So that means directed that edges, and each edge contains three values. So one is start point, and this is the destination point, and this is the weight of the edge. So now for the graph, these are some edges we have. So this D edges is representing a set of edge. Now how we are storing this into a our graph? So that you know that we use the adjacency matrix representation, and we use the adjacency list representation for the graph. For adjacency matrix, you can see now we are creating a matrix using numpy. Okay, you can also create using a nested list, that Python nested list. But here what we are doing, we are creating a matrix of this size by comma 2. So here that means we are creating it like three-dimensional matrix. So each cell, so this, suppose this is a row, so this is a row and this is column. Okay, and each that row and column cell, this point is also a some dimensional part, so that contains two value. So the size is 2 actually for this. Okay, so initially this is a zero matrix. After that we are traversing all the edge, and for each edge you can see I is the source vertex, J is the destination vertex, and W is the weight for that edge. So for each we are just we are traversing all these edges, and in our matrix we are putting one value for the, that means this one this at this each location. So in each cell we have a list. Okay, so or we can say that we have a tuple. So tuple like this, and what we are doing for first index. So we have two index here for each place. Now first index we are writing 1. So this 1 is representing that there is a one edge from I to J. Okay, so this I is representing a row and J is representing a column. So from I to J we have one edge, so that we are marking as a 1, and second value in this data structure at this point we will store the weight. So you can see 0 index we are storing 1 means edge is there, and 1 index we are storing that W weight of the edge. So like if we are storing this 10, so this 10 will be stored like, okay, for this I and j position. So in this way, our matrix will be created. So like for each row column combination, so we will get the value like this. So 0, comma, and 0. So if there is no weight, so that means 0. And another combination like 1, comma 0, sorry, 1, comma 10. If edge is there, some weight will be there. So in this way, this edge matrix will be created. Okay, so each value of the matrix contains two value, either 0 for no edge and 1 for edge. If edge is there, then weight it will also be stored. So in this way, matrix will be created. That matrix will called as a adjacency matrix representation. Another way to represent this directed graph, then weighted directed graph, is adjacency list. So this is very similar to the previous one, but this time we will also store the that weight. So same things, d edges. Now you have this edges, directed edges. Now this is the size, and after that we are creating a dictionary. Okay, WL, you can see this is a dictionary, and for each source, you can see we have this I and size we have 7, so 0 to 6. That means these are the vertex name for this graph. And for each I, that means for source WL for I. Okay, so 0, then similar to 1, we are creating a dictionary. Initially, we are just passing a empty list as a value. So this, the value of the dictionary for each vertex is representing a edge which are connected from this source 0. Okay, and here inside this list we will store the tuple, and that tuple will contain two value. So you can see, for we are just traversing the edge, and for each I, so I is, we will check for this first value, and j will be considered as a second value. So for each combination, we are just writing that what is the destination and what is the weight for that destination. So how many edges are going from this 0? So you can see 0 to 1. So this data will be represented like this. So WL in dictionary. So for 0 key, we will have a list, and in this list, first tuple will contain. So that means 0 to 1 edge is going. So that 1 will contain, and what is the weight? So 10 will come here. Okay. So this is representing a one edge from 0 to 1 with weight 10. Another is 0 to 2. So you can see another tuple will come in this list. So that will contain 2, comma 80. Okay. Now you can see there is no edge is going from 0 to any one edge vertex. So that means this is the key 0, and this is the list of tuples where each tuple is representing a one edge that is a destination from 0 with weights. So in this way, we are storing the data, and we will store this information for each vertex. So what is the edges for from 1, then 2, then 3? If there is no edge from any vertex, so that list will remain empty like this. So in this way, we are storing our graph information in the adjacency list form. So this is for directed graph. Similar things we will do with the undirected graph. So undirected means just for each edge, we will just store the information from both sides. So suppose here this is a directed edges, but this is a undirected graph. So for this edge, so 0, 1, 10. So this edge will not be considered as a only from 0 to 1, because this is an undirected graph, there is no direction. So we will store the information from both sides. So that means 0 to 1 as well as 1 to 0 with 10. Okay, so each edge will be represented by two value in the matrix, 0 to 1 and 1 to 0, both direction. Okay, and both direct edge weight is 10. So that means for each edge, we will contain two information. So like this is a edge, and this is also a edge in the undirected graph. So because of that, you can see first things we are updating the edge list. So for this directed edges, we are changing, and we are also storing the another side of the edge. So, okay, so this is I, j, w. For this, we are also adding j, I, w in the edge list. So now this edge list is now a complete list for the undirected graph edge. Now after that, we will do the same things. as the previous. Okay. Similarly here, so first we will add the information from both sides. So 0 to 1 and 1 to 0. Both information should be there in our data structure. So that we are storing in our a dictionary. So in this time, if any edge is there 0 to 1, this edge is connected. So it will come in the dictionary like this. So that 1 with 10 like this. Okay, suppose weight is 10, as well as the same information will come from the one side. Okay, so that 0 comma 10 like this. Okay, so that means 0 to 1 with weight 10 and 1 to 0 with weight 10. So both information will be stored in our data structure. So this is the way to store the information about the vertex and that edges of the graph in our data adjacency list and adjacency matrix form. So this should be very clear when we are just dealing with this directed weighted graph or undirected weighted graph. Okay. So any query in this representation? How we are representing the data, the direct this weighted graph in our adjacency list or adjacency matrix form. Okay. So now comes to the main algorithm. So first topic is shortest path. So shortest path is very common application in our real life. So you know that most of you are using this Google Map things. Sometimes you search the location. So you just enter the destination name, and that map is actually show you the shortest path or maybe multiple paths, and that graph is actually so based on the some traffic information also, where is the less traffic, where is the more traffic. So that is also showed the details with the based on some parameters. But sometimes if you want to find out the shortest path, so that map will also show you the shortest path. What is the shortest path possible? Because there are multiple paths from one source to another destination. So among all these paths, which one is the shortest? Okay, so this is the problem. Now for to solve this problem, okay, so we have these algorithms. So first is single source shortest path. So this is the one category to find the shortest path. So that means these two algorithms are defined to find out the single source shortest path algorithm. So that means we will give one source to the algorithms, and for this source, what is the shortest path for each destination. Okay, suppose we have like A, B, C, D, E. These are the destination point or vertex in the graph, and we will pass one source. This is a source, and from this source, what is the shortest path for each A and B and C and D and E? We will calculate this information. So this is called as a single source shortest path algorithm. Okay, here we are just giving a one source, and then all will another vertex will be considered as a destination, and we will find out the shortest path for each destination from single source. So for this category, we have two algorithms. One is Dijkstra algorithm, another is Bellman-Ford algorithm. Okay, so both purposes same, but these algorithms have some limitations. So we will discuss this. Another category we have this all pair shortest path. So I'm just giving this. We will discuss it. Okay, so that will come later in these notes. But all pair shortest path means that we have one algorithm for that. That is Floyd-Warshall algorithm. And all pair shortest path means we will run this algorithms on the graph, and that algorithms will return the shortest path between every pair of the vertex. So suppose if you have this set of vertex in the graph A, B, C, D, E, so that means that algorithm will return a shortest path from each pair. So like A to B. Okay, so for what is the shortest distance between A to B? Similar to A to E. So this is also a one pair. So what are the possible pair for this? A to B, A to C, A to D, D to E, like this. So for each pair, this algorithms will calculate the shortest path. Okay, so because of this is called as a all pair shortest path. So that is Floyd-Warshall algorithm. Now let's discuss this single source shortest path algorithm. So first is Dijkstra algorithm. Okay, so Dijkstra algorithm basically a we can consider as a greedy algorithm. So what is greedy algorithms? We will discuss this. Hmm. So what is the algorithm's steps for this? We will understand this. So let's, this is a graph. Let me copy this and okay, so here I'll can mark okay once. So suppose this is a graph, okay, and we are considering that this 0 is a source vertex. Okay, so this is a source vertex. Okay, and we want to find out the shortest path from 0 to each vertex. So this 1, 2, 3, 4, 5, 6. What is the shortest path value for each vertex from 0? Okay, so how this algorithms work actually? So we start from the 0, and because this is a source, we consider as a the distance from this 0 to 0 is 0. Okay, so we will initialize this 0 distance for source, but initially we will initialize the infinite distance for each vertex. Okay, we are just initializing this value as a shortest path distance for each vertex other than source. So this is the point first. This is the initialization steps. Okay. Same things. Initially, we will consider as a all vertex are not visited. Okay. So we are marking this that all visited, all vertex are not visited from source. So these are two information we store initially. And after that, what we will do? We will start the process. So what is the process? We check that. So you can see we have initialized the distance. Okay, distance from source. So 0, we have this 0, and remaining are infinite. So first we will consider that which vertex have the minimum distance from source among all these. So you can see now this vertex have the minimum. Okay, source 0. All remaining are infinite. So this is the minimum 0. Now we select this vertex. And after selecting this vertex, we check what are the adjacent of this vertex. Okay, what are the adjacent of this vertex? Means 0 to 1 and 0 to 2. So these are two adjacent where we can move. 0 to 1 we can move, 0 to 2 we can move. And when we are moving by this edge, so what distance, what weights we are getting on the edge? Okay, so that we will consider, and we will also add the previous distance on the node. So at that 0 source vertex, what is the current distance? This is 0. So we will consider that 0 plus. So I'm considering this 0 to 1 edge. Okay, so what is the distance value for this? 0 to 10, 0 plus 10. This is equal to 10. So for this one, we will check. We are getting 10 distance from source. Okay, so 0 to 1 we are getting 10. Is this is lesser than to the previous assigned value? So we will check this condition. Okay, so what is the current distance we are getting from the current vertex to when we are moving to the by this edge? So we are getting previous distance on 0 plus 10. Is this 10 is less than to the infinite? If yes, if it is smaller than the previous weight, okay, so then we will update this. Okay, so 10 you can see this is smaller than infinite, so we will update this 10, and this 10 is representing the shortest distance from source. Okay, and similarly we will do this for the another adjacent. So 0 to 2, and 0 to 2 is previous distance on 0 is 0 plus 80. This is 80. Now this 80 is less than infinite, previous distance on 2, this one. Okay, so now we will consider this 80 as a minimum distance from 0 to 2. Now we will update this. Okay, and when we are visiting this 0 vertex, then when we are doing this process, so we will mark this as a true. Now we have visited this 0 vertex completely. Okay, and remaining are false. So this is the process we will repeat with every vertex. Okay, and we will again find out the same things, and figure we will repeat this until our all vertex is not visited. So now let's see next iteration. Okay, so this is the first step. Now you can see in the remaining unvisited vertex, which one have the minimum distance? Now you can see this, I'm writing here. Okay, so 1 0 1 2 3 4 5 6. Initially all are 0 and this is infinite. Okay, now after first process we are getting 0, and for 1 we are getting 10, and for 2 we are getting 80, and remaining are infinite. Okay, now you can see we have already selected this, so this is done. Now the remaining vertex. Okay, so remaining vertex, you can see 1 2 3 4 5 6. We have the smallest distance is 1, this vertex. Now we will select this. Okay, that means we will select this for the next process. So when we are selecting this, so the shortest distance at this point is 10 from source 0. Now we will check the same things and we will mark this as a true, because now we are visiting this, so we will mark as a true. Now from 1 where we can move, so from 1 you can see what are the adjacent of this. So 1 to 4 we can move, 1 to 2 we can move. So when we are moving 1 to 4, so what distance we are getting, so that we will add the previous distance also, because our final goal is to find out the shortest distance from source. So because of that, what is the shortest distance on 1, then we will add this. So 10 plus, and 1 to 4 is 20. This is 30. Now 30 is less than infinite. Yes. If this condition is true, then we will update this. So this will become 30. Okay. Now same things from 1 to 6. So 1 to 6 is 10 plus, sorry, 1 to 2. This is the 6. Okay. So 10 plus 6 is 16. 1 second. So this is 16, and 16 is less than infinite. No, 80. Previous is 80. So now we will update this by 16. Okay, and this is now process. So you can see when we are selecting this one, so in next cycle, this is the updation. So 10, this 80 is now become 16. Okay, and this 3 is not updated yet, so it will remain infinite. 4 is now updated by 30. Okay, and this will remain infinite. Okay, so now you can see these two have already selected. Now remaining are 2 3 4 5 6. So which one is the smallest? Then we will select 2, this one. Okay, this 16. Now from this we can only move to 3. Okay, so what is the smallest distance till here is 16, and 16 plus 70 is 86, and which is lesser than the infinite previous value. So then we will update this by 86. Okay, so now this is the next updation when we are selecting 2, and that this 2 will be marked as a true. Okay, and this is the next. So 0 10 16 and 3 is now updated to 86, and this 30 remains same, and infinite. Okay, now this is done, this is done, and this is done. Now remaining are 86 30 infinite. So same things we will do again. So 30 we will select. So 30 is the smallest now, 30 is the for 4. So then we will do this. So we will mark this as a true. And what is the movement from this? So 4 to 5 we can traverse, 4 to 6 we can traverse. If we are traversing 4 to 5, so that means 30 plus 50. So this is 80, which is lesser than the previous value, so infinite. Okay, so 80 we will update. Okay, same for 4 to 6. So 4 to 6 will be that 30 plus 5, which is 35, which is lesser than the previous value infinite. So we will update this 35. Okay, so this will become 35. So now this is the next updation. So 0 10 16, and this is 86 and 30, and that 5 is become 80, and this 6 is now 35. Okay, now this is already done, this is done, this is true, and this is also marked as true. Now remaining are 3 5 6. So which one is the smallest? Then 6. So this node will be selected next for the traversing. Okay, so we will mark this as a true, and we will check there is no outgoing edge from the 6. So no updation will happen when we are selecting this. So same will remain same. So 35 is done. Now what is the next minimum is 80. This is for 5. Okay, so from 5 you can see we have the outgoing as 5 to 6, but here from here we are getting 80 plus 10, which is 90, but 90 is greater than the previous value 35. Okay, so that we will not update because we are not getting a smaller value, so we will remain the same previous value 35. So that means no update is again, so this will remain same. Now 86 only remaining, so there is no outgoing as for 87. Okay, so this will become true. So in this way 36, this will be the final one. So finally, after the repetition this process, what value you are getting in this distance, okay, in list which you are maintaining. So this is representing a shortest path value from 0 source vertex. Okay, so that means from 0, for 1 the shortest distance is 10, for 2 shortest distance is 16, for 3 shortest distance is 80. Okay, and for 4 shortest, sorry, 86, for 4 shortest distance is 30, 5 shortest distance is 80, for 6 shortest distance is 35. So this is the way to find out the shortest distance by the Dijkstra algorithm. So now you can see this is a greedy algorithm. So greedy algorithms means for each steps when we are just looking from the overall optimal solution from 0. So for when we are selecting this 0 vertex for starting, we are selecting the optimal solution. So you can see in every cycle we always select the vertex which have the minimum distance, and after that we check the, we are also updating the distance if we are getting smaller than to the previous one, then we are updating. So that means for each steps you are getting the shortest path for adjacent. Okay, so that means you are trying to figure out the optimal solution at each step. So that is called as a greedy approach, where you are just figuring out the optimal solution at each steps. So that because of that, this is a greedy algorithm, and this is the working of this algorithm. Okay, so now if you see the step, so this is some visualization you can run. Okay, and this is the code. So let's discuss this code, how this code is working. So let me discuss the same. Hmm. Hmm. So the code is given with the adjacency matrix as well as the for adjacency list. Okay, so for adjacency matrix. So what we are doing, you can see in the code, this matrix we are creating. So this W mat is actually we are passing in that numpy matrix for the code. Okay, so you can see what we are passing in the function. So this is Dijkstra algorithm W and 0. This second value is a source vertex 0. Here W is a that matrix which is created by numpy, and that contains 3 dimensions. So that is actually a row columns X. Okay, so now we are calculating this infinite value. How we are calculating this infinite? We are finding out the maximum value in this WMAT matrix, and after that we are multiplying the number of rows and plus 1. So we are calculating some bigger value which is not possible for any distance. Or in Python, what you can do, you can also create a infinite with the help of this INF. Some okay, there is a feature in Python. You can also assign the infinite value. Otherwise, here we are calculating the maximum possible value, which is not possible for any directed that path value actually. Yes, someone is.
Yes, one question. Generally, sometimes we are given the vertices and the edges,
Mhm.
and we are not told whether it's directed, undirected, and then we
Mhm.
said find the path. So, do we by default take it as undirected or do we take it as directed?
Okay, no, I think it will be given. This graph is it directed or not? So where it is not mentioned.
Sometimes I think in some of these earlier questions we had in these weeks,
But yeah,
if
that
the edges
actually
are given and vertices are given, and then they said find the whatever that.
so if suppose if direct data structure is given and you have the matrix or you have the that adjacency list, so that actually will contain this information. So if graph is direct undirected, so that means that matrix will contain from I to j. Suppose so I to j, you will get 1, and same for j to I, you will also get for 1. If you are getting the both side from both side, okay, edge, for each edge I comma j, you will get the both entry, okay, I to j and j to I 1 in the matrix. So that means graph is undirected.
So it will
But
be, so we don't have to assume anything. Whatever is given, we just have to go with that.
yeah, so that if you so this direct algorithm you can apply, doesn't matter what type of that graph you are getting. Okay, so it will work. Okay, so actually this that data structure contains this information. So what type of graph? Okay, so if both entry are there, so that means graph is undirected. Otherwise, if for each edge, if I to j is entry is there and j to I entry is not there, that means there is no edge. So that means graph is directed. Okay, so consider this as a directed graph. So why we are saying that undirected graph? We can also consider the undirected graph also a directed graph. So suppose this is a and this is a B, and edge is connected, okay, with 10. So we can also consider this as a directed graph like this, 10 and 10, okay, like this. Okay, so here undirected means you can traverse A to B or B to A also. There is no direction. So that means this is equivalent to the directed graph of like this, where you have the edge A to B with 10 and B to A with 10. Okay, so because of that, this algorithms work for both. Okay, so these things infinite we are calculating. By this we are finding out the maximum weight in the matrix, and after that we are multiplying by the number of rows and plus 1. So that means we are calculating some bigger value, so that is not possible for any path. Okay, so you can be calculating this way, or you can also define infinite directly in the Python. So after that, what we are doing, we are maintaining these two parameters which I have discussed. So one is visited and another is distance. So visited and distance both are dictionary. In visited dictionary, we will maintain this two, that node is visited or not. Okay, and distance we will maintain the shortest distance from source. Initially, we are assigning some value. You can see for each vertex, we are assigning false, that means not visited, and infinite for distance. Okay, after that for source, you can see we are assigning the value of distance is 0 for source. Okay, so this is the next step we have discussed. We will consider source as a 0 distance. Now we will repeat this process. So after that, for u in range row, so we will repeat this process for each vertex. Okay, so how many vertex we have, we will repeat. So for u in range, number of rows, and number of rows is representing number of vertex. Okay, and for each cycle of for each iteration of this loop, we are figuring out that which vertex actually can have the minimum distance. So you can see this is the way what we are figuring out, the distance v for v in range row if not visited. So the vertex which are not visited, we are finding out the minimum distance first. Okay, so in this line we are figuring out the minimum distance value. What is the minimum distance value on the vertex which is not visited? Okay, this is then after that, then we will figure out that which vertex actually contain that minimum distance. Okay, so this is next cycle. that next instruction. So this is the list which actually contain. So there is a possibility that minimum distance is coming on more than one vertex. So we are figuring out all the vertex which have the minimum distance value. Okay, suppose you are getting the minimum distance 10 on the in the all vertexes, okay, which are not visited, but we are not sure that this 10 is already a minimum distance for one vertex or maybe more than one vertex. So we are figuring out the all vertex list which contains this 10 distance, okay, which is minimum. After that we will figure out the minimum. So suppose we are getting three vertex like 3 and this is the label of the vertex, okay, so 3 5 8. So these three vertex are actually all contains the 10 distance from source. Okay, now we will figuring out the minimum label. So what is the minimum label for the vertex which have the minimum distance 10? So that means we will pick this third vertex, okay, to the next cycle. Okay, now we will, after picking this next v, which is the minimum distance vertex, then we are marking that as a true. Okay, and then we are updating the adjacent distance. So you can see for each for v in range column, so this is a matrix, so we have to traverse complete columns of the matrix to figure out the adjacent. So for v in range columns, if w met next v comma v comma 0, so you can see in adjacency matrix we have this information. So for each source to destination and the first index, if this index is 1 and if the vertex is not visited, if this v, so from next v to v, so this is v is actually adjacent of next v, if this is not visited, then we will update the distance for that. So we will check that distance of next v plus the edge weight is less than the previous distance of v. If this condition is true, then we will update the distance of v to new distance. Okay, distance of next v plus edge, if this condition is true. Okay, so now we are repeating this cycle for each vertex. Every time we are selecting the minimum vertex node and then we are checking the neighbors. If neighbors are not visited, then we will update the distance if we are getting the smaller distance to the previous distance. Now we are updating. Okay, so after completion of this for loop iteration, and finally we are returning this information distance. Okay, so this is actually a dictionary that will return you the information like this. Okay, so 0, this is the source, and source to what is the shortest path distance for source is 0. For 1 you have 10. Okay, we have already calculated this in the previous example for the same graph. So you can see for 2 we are getting 16.0. So you can see in this, yeah, so 16. Okay, so 216. For 3 86 30 80 35. Okay, so same we are getting, you can see 86 30 80 and 35. So we are getting the same. Now the same logic we will use. Yeah, someone, okay, please ask.
So we've got the minimum distance for each vertex, but shouldn't we also know from which vertex it is the minimum distance?
Oh, 1 second. Okay, so where is the page? From which vertex? So this that here we are calculating the shortest path from source. So this minimum distance is actually from source.
But if we just see the
This
output, we don't know what the source is, right?
source is 0. You can see when we are calling this function, we are passing second parameter, which is actually a source.
Okay.
0. Okay, if you passed 1 here, that means 1 will become source.
Okay. Got
So
it.
all these distance are actually from 0 vertex, complete path distance. And this is a minimum path, that shortest path distance means. Okay, you cannot figure out the more shortest compared to this. Okay, because of that, this algorithm is a single source shortest path. And same you can figuring out using the adjacency list. Now we are changing that data structure type. All step will remain same. So here same things, we are maintaining this visited and distance, or you can directly calculate the infinite. Okay, so Now same we are initializing. After that, here for u in w list keys. So number of keys in the dictionary is actually representing the number of vertex in the graph. And after that, you can see main list and next we list. All steps are same. And the finding the neighbor is actually the different process here. So for VD, in here we can directly figuring out the neighbors with the help of value of the key. Okay, so W list next V. So this is the key. For this key, what value we are getting in the value, which is actually a list of tuples. So we are getting this list of tuples here directly. This is representing a neighbor, and for each neighbor we are checking that if the distance of next V previous distance and plus the edge distance is less than equal to the distance of V. Okay, if this condition is true, then we will update the distance of V to the new distance, otherwise nothing. And after that we will get the distance dictionary with the shortest path from the source. Okay, so same data is there and same output we are getting with the adjacency list. Okay, so yeah, this is the steps for Dijkstra algorithm. So this dry run should you know that in for example the questions asked in the exam, some graph is given. So what is the shortest path from each? And sometimes the important question is asked like that: what is the order of visited node? Okay, so in which order we are visiting the node? So in the previous example, when we apply the dry run on this graph, so first vertex is visited, which is a 0. Okay, after visiting this, we are getting the distance on 1 and 2, and the distance on 1 was 10 and another was 80. So next node we visited 1. So what is the order of vertex which is actually visited? In which order we are visiting the vertex in this Dijkstra algorithms? So this is also a one possible important question which is generally asked in the question that exam. Okay, so you should know that dry run process on the graph, how the algorithm is actually works. So do not remember the code, but you can just remember the steps, how we are just applying the algorithms on the graph and how this is calculating the shortest distance. So if you know this, then you can also write your implementation. If you know these steps, do not learn, no need to learn this given implementation, just write your own implementation. Okay, yeah, so this is Dijkstra algorithm and this is for both. Now next is Bellman-Ford algorithm.
Sir, in this, at any given stage, from one node to the next node, the shortest one will be selected. No? I joined little late. Just if it is discussed, I'll go through the recording later.
Yeah, so every time if we suppose if we are looking from here, so 0 to when we are just traversing 0 node. Okay, so from 0 where we can move 1 and 2. Okay, so we will check what is the current distance on 0 and we will add this value 0 to the edge value 10. Okay, so 0 plus 10. If this distance is less than to the previous distance on 1, okay, so then we will update, otherwise we will not update.
Okay, so okay, we are kind of tracking all the path, and at that stage, whichever path is shortest, we select that path.
Yeah, so we are maintaining this distance value for each vertex. Initially we start from the infinite, okay, for each vertex, and during the process if we are getting less value to the previous value, then we will update.
Okay.
Okay, yeah, so in this way this is working. And same things, now we are getting the shortest distance and you can also track the path. So how you can track the path? Now in this algorithms we are not tracking the path. Okay, so we are only getting the final shortest distance answer, but we cannot reply the what is the path. So how you can that find out the path, because this is also a one problem. So suppose if it is asked that what is the possible path for this minimum distance, so how you can figuring out? So you have already done similar type of things in the previous week with the BFS and that algorithms. Okay, so you can, if you can maintain this information, parent information. Okay, so where from you are getting the minimum distance, if you maintain this information as a parent information, so then you can also track the path. So that means when we are starting from 0, so this is a source, and yeah, so this is a source, and when we are traversing next node, okay, so this is now we are traversing from 0 to 1 and 0 to 2, and we are getting the smaller distance. So okay, 810, which is less than to the infinite value which is previously assigned. Okay, at this point what you can do, you can also maintain one parent dictionary. Okay, parent dictionary, and where for each vertex, if you are getting this information, so 10 is less than infinite, when you are updating the distance. Okay, so at that time you can also update this information where from you are getting this 10. Okay, so you are getting, so that means for parent, that means for this, what will be the parent for 1 is 10, that 0, sorry, 0. Okay, so you can store this information because you are updating that now the 0 to 1 minimum distance is 10. So where from you are getting 10, that is 1. So that information you can store during the process. Same things for 2, you are getting 80. Okay, now in the first cycle, so 80 you are getting from 0. Correct, fine. Okay, but later when you select this one node in the next cycle, so from 1, this is the 10 distance on 1, and 10 plus 6 is 16. 16 is lesser than 80. Okay, now you will update this 80 by 16. Now what is the parent of this 2, which is updating 16? Okay, so now this is 1, so this parent will update like this one. So if you maintain this parent information for each vertex, so now you can also track the path for each. Okay, so where you need to update this information, so I think it is not given. Okay, but you need to just maintain in the code like this. So here you can assign one parent. Okay, so one more dictionary parent, and you can also assign with empty dictionary. Okay, initially for each parent you can assign a -1 value. What is the parent for each vertex? Okay, so parent, so in this line, okay, for each vertex you can also add the parent of v. So like this, parent of v equal to -1, like this. Here you can pass -1. So -1 will assign as a parent for each vertex, and later where you need to update this parent in this state. Okay, this line, if this condition is true, so here you are updating the distance. Okay, distance of v equal to distance of next this. So this distance you are getting from next v node. So at this point you can write like this. So parent of v is equal to next v. Okay, this next v. So this is the only update required for in this code, and now you will get this parent information for each node finally, and you can use this parent information and you can find out the path. So for path calculation, if suppose if you have this parent information for each node and you want to find out what is the path from 0 to 6, okay, so you can just use the backtracking. So just check what is the parent of 6. Okay, so what the parent of 6 is, suppose if you're getting 4, so now 4. So what is the parent of 4? Okay, so that you will just find out, like suppose this parent of 4 is 2, and what is the parent of 2, and you are getting like 0. So you can traverse from the destination and just check what is the parent, and in this backward form you will repeat this process until you are not reaching the that source node. Okay, and just stop the process if you are finding the parent equal to source. So in this way you can figuring out the path as well. Okay, so what is the path for shortest distance? Okay, so this small update is required. So just maintain one dictionary, initialize one dictionary, initially assign with -1 for each parent, and update this value here when you are updating the distance. If you're getting smaller distance and you are updating the distance, at that time also update the parent. So this is the updation required. And we have already done this type of problems the previous week, live coding problems also, and maybe some assignment also. So you can do the process, this backtracking.
Sir, one more doubt in quiz and in this OPP exam, if
Mhm.
any question is coming from this particular topic, let's say,
Hmm.
so what kind of question will be asked in that?
So for Dijkstra algorithm, I have mentioned that this order of visited node that is actually asked in many time. Okay. So in what order we are visiting the vertex in the Dijkstra algorithm?
Oh, you meant to say this output. This is the order of vertex we are visiting, right?
No, no. So that we are also maintaining one dictionary now. So this is visited each time when we are selecting the minimum distant vertex. So at that time we are marking this vertex as a true. You can see
Hmm.
visited next be equal to true.
Hmm.
So in which order we are marking these vertex as a true? So initially we are starting from zero vertex. Next time which node is selected? So suppose this one is selected. So that means one is coming. And after this one, which node is selected as the next minimum vertex? So this order actually asked. Okay.
Okay, so that's a dictionary with the key is that vertex and the value is true, right?
Hmm.
Once it is added.
Yeah, it is added to the process.
Okay.
So what order actually we are getting for the vertex, which in the visited form? So which order these node are visited actually? Okay, so this type of question asked in the Dijkstra algorithm. Otherwise, the shortest path distance. What is the shortest path value for destination from source? That type of question is asked, and yeah, some constraint is also there. So that is also important. This Dijkstra algorithms is not works for negative weight cycle. Okay, so it always works on positive weights. If all edge contains the positive weights, then this algorithm will work fine. Okay, but if this graph have contains the negative weights, not negative weight cycle. Okay, I'm saying that negative weight. So this is difference. If there is negative weights means, suppose if graph is given like this, so S and like this A and this B like this. Okay, and this contains like 10, this is minus 20, and this is 30 like this, and another graph is connected. Okay, maybe further. So here no cycle is there, like the C is there and D is there. Here no cycle is there, but one edge is contain negative weights. Okay, so this is not a negative weight cycle. So in that case, this Dijkstra algorithm may work or may not work. We are not sure that that algorithm will work or not work. So sometimes it may fail. Okay, so generally we say that this Dijkstra algorithm not work for negative weights as well as negative weight cycle, but for negative weight it may also return the correct output in some case, but we cannot use always for negative weights. Okay, but so that we will discuss the example when it actually maybe return the correct output for the negative weights, but definitely for negative cycle it will return a incorrect output. Hmm. Okay, so let's discuss one example. So where actually it fail actually. Okay, so let me open here. Suppose you have a one graph A, and this is the distance like B and C. Okay, and this is 10, and this is minus 8, and this is 5. Okay, so I'm writing one graph here. This is very small graph, and we apply the Dijkstra algorithm on this. Okay, so are we will get correct output or not for this. Okay, so what we will do, we will start the suppose this is a source A. Okay, and we start this 0, infinite, infinite, same process. Now when we start from A, we are visiting this A, and from A we can move to B with 10, and we can move A to C with 5. Okay, so 0 plus 10, 10, which is smaller than infinite, so this will update by 10. Correct. And for A to C, we have 0 plus 5, 5, which is smaller than infinite, so this will update by 5. Now this is marked as a true. Now, which node will be selected next? So this B, these are actually false. Both are not visited yet. So here B and C both are not visited, and these contain 10 and 5 distance. So which node will be select next? C, because
Yes, sir. Shortest.
yeah, shortest distance, minimum distance. Okay, so this 5 will be selected because this is the minimum in unvisited vertex. So we will select next C. And when we are selecting next C, so there is no outgoing edge. So there will no update happen from C. Okay, so that means now this is visited as a true, and only remaining is B. Okay, now we are selecting then B, but you can see we always update the distance of the nodes which are not visited. But from V, when we are selecting B, and the current distance of B is 10, now you can see there is one outgoing edge is there, and that is contained -8, and 10 plus that -8 will become 2. Okay, and this 2 is smaller than previous distance 5. Okay, but we cannot update this because this node is already visited previously. But logically you can see that shortest distance from A to C is 10 minus 8 is 2, but by Dijkstra algorithm process we are getting 5. So this type of situation, our Dijkstra algorithms actually become fail with the negative weights, because Dijkstra algorithm never looks back to the node which is already visited. That actually Dijkstra algorithm not update that vertex. Okay, and the same thing, suppose that we have the graph like this, so A to B, and this is C, and this time I'm changing this like this, so 5 and 10, and suppose let me select 8 and yeah, so like -4, like this. Okay, so again the graph have the same things. Okay, but this time also contains the negative weights, but this time 0, infinite, infinite, and you are getting, you can say that A to B is now it will update by 8, and now A to C will update by 10. Now which node will be selected next? B. Okay, this time V. So this node will be selected. Now C is not traversed yet, visited yet. Okay, so we will check from B. So 8 minus 4 is 4. So that will be updated by here. Okay, so now this is updated, and so this is done. Now from C there is no outgoing edge. Now you can see with the same negative weights, we are getting the correct output. Okay, logically this is correct. So A to B is 8, A to C is shortest path is A, B, C, then this is 4, and this is the correct answer. Okay, so that means how we can figuring out this. So if that means if you are traversing any node and you are getting smaller distance to the previously already visited node. So in this previous example, here we are coming from this vertex, and we are getting a smaller distance from this B to next node, but which is already visited. If this type of situation we are getting, and we are going to the vertex with the negative edge, and we are getting the smaller distance to the previous distance, but that node is already visited previously. In that case, we will get the incorrect output. So that means if our negative edge weight is coming from the currently visited node, so this node we are currently visiting B to already visited vertex. So that means that unvisited vertex to already visited vertex. If we are going like this with the negative weights, if this negative weights are coming on the edge which is coming from the currently visited node, so at the current node to the visited node, then it will return a incorrect output. If this negative edge is coming from the current visited node to the unvisited node, then it will return a correct output. it will update this. Okay, so these are the case if graph have negative weights. So we can say that our graph, that our algorithms may work correctly or may not work. And if this is the conclusion that we are not sure that if our graph algorithm will work, always work correctly, so then we generally say that graph is, that algorithm is not work for negative weight also. Okay, so this is the conclusion. That means Dijkstra algorithm not works always correctly for the negative weights and not works for the negative weight cycle. So negative weight cycle means if you have a like this A and you have the cycle also, so B and then C, and you are repeating this, and you have like this 10 minus 16 and 2. Okay, so suppose if you are starting from here and you are adding this 10 plus minus 16 plus 2, so overall sum you are getting negative. Okay, so here you are getting -4. So this is called as a negative weight cycle. If you are getting overall sum is negative, so this is called as a negative weight cycle. In this case, this Dijkstra algorithm will not work. And for this type of situation, actually no algorithms work, because here what will happen? This cycle will run in that infinitely. Okay, suppose if you are updating the distance, so you are updating A to D10, and 10 to here you are getting minus that 6, and when you are updating this -6 to A, so that will update again to -4, and from here -4 to 10 again it will become -6. Then this cycle will run. Okay, and you will always get lesser value. Because of that, you will that algorithm will never steps and you will not get the final correct answer for this. So for this type of situation, actually our algorithms, no algorithms works actually. Okay, for the Dijkstra algorithm also not work, and Bellman-Ford and that float Varsal also not work. But for negative weights, we can say that that Dijkstra algorithm not works, but Bellman-Ford actually handle the negative weights, but not negative weight cycle. Okay, so this is Dijkstra algorithm. Any query in this? Okay, so let's move to the next, that Bellman-Ford algorithm. Okay, so Bellman-Ford algorithms runs correctly on the negative weights, but not negative weight cycle. Okay, so these properties are given here. Also, it can handle graph with negative edge weights. It can detect a negative weight cycle. It can handle disconnected graph. It use dynamic programming. So that we will discuss later. So when the dynamic programming will come in our syllabus, that we will understand this, what is dynamic programming. Okay, so how this actually Bellman-Ford algorithm works. So this is actually takes more time compared to the Dijkstra algorithms, but the implementation is easy for this. Here you can see we will use a 3 loop. So for I in range row, then for this row. Okay, so that means overall complexity will become a VQ. If we have total V vertex, so you can see we are getting overall complexity VQ for this. So how this algorithm is working actually, and this is repeating the iteration. So let me take graph for this. Okay. So this is negative weights. Okay, let me take this. Okay, so actually we will repeat the complete process. So how many vertex we have? So we have total 8 vertex in this. Okay, so 8 vertex in this graph, and so that means we will repeat the process 8 times on this graph. So this is the first loop actually representing. So we will represent the updation process 8 times. Okay, so what is the updation process? So first we are selecting the vertex 0. So for first cycle. Okay, so you can see in the graph. So initially this is the initialization. So infinite value we are assigning, distance we are maintaining, For distance v equal to range rows distance, we are maintaining the distance with starting with infinite, and source distance is assigned by the 0. Okay, so same things we are doing here. So we are just starting with 0 distance for this, and remaining are the infinite, like this. Now, and you can see the first loop. This is representing the number of iteration for the same process. Okay, so this is depends on the number of vertex. Okay, now for each, check for each adjacent of u vertex. So you can see for u in range row, so that means we are traversing each vertex, and for v in range columns. Now we will check if okay. So here actually this is the main thing. So for u in range rows, okay, for each vertex, v in range columns. So we are looking the all columns. If uv edge is there, then we will update the distance. Okay. Okay. Yeah, so what we are doing actually, so we are starting from 0. Okay, so 0, what are the adjacent of this 0? Okay, so for each adjacent of 0, so that adjacent of 0 are 1 and 7. So we will update the distance from 0 to 1. Here we will add the distance from the current vertex 0, and what is the edge distance. If it is smaller than the previous distance, then we will update. So in this first cycle, okay, so we are repeating this process 8 times. So in first cycle, we will check for each node. We will check for each node, and we will update the distance for adjacent of each node in the one cycle. Okay, so that means for 0, we will update this by 10. Okay, so you can see 0 to 1, we are getting 10. So this is the first updation. And 0 to 7, we have this 8. So this will update by 8. Okay. So now this operation is happened for 0. Now 0 is done. Now 1. So we will check for 1. So now here we are not selecting anything like this, which one is the minimum shortest distance. Okay, we will repeat the complete process 8 times. So that means for each vertex, we are selecting the vertex and we are looking the adjacent for that, and we are updating the distance. And we will repeat this cycle 8 number of times. So we will check the number that one vertex. Okay, so one vertex, what are the adjacent of this? So 1, 2, you can see you can move to 5. So 10 is there, 10 plus 2, this will become 12, smaller than. Okay, so now this is the updation for 1. So this changes happen from 1, and there is no outgoing edge. Now you will look 2. Okay, so we are not checking this like minimum distance vertex here. And now for 2, you can see the current distance is infinite. So if you will add this anything in the infinite, or you will subtract anything from the infinite, so that means you will get the infinite. So if any edge is going from this infinite, okay, so 2 to 3, so that means that will remain infinite. Okay, so from 2, there's no updation is happening. From 2 to 1, you can see infinite plus 1, that will also remain infinite, but previous is 10. We will not update this. Now 1 is done, 2 is done, now 3. Okay, so now 3, we are looking 3 is currently infinite, so no update will happen. Okay, now 4, vertex 4. So 4 vertex is here. So again same things, it is now infinite, so no update will happen. So 5. So 5 is not 12. So from 5, what is the outgoing edge? So you can see 5 to 2. Okay, there is one outgoing edge. So 12 minus 2 is 10. So this infinite will will update by 10. Okay, so this 2 is updated from this. Okay, now no outgoing edge. Then we will check for 6. So 6 is infinite, same things, nothing will happen. Okay, so 7. So 7 is 8, and from 7 you are moving to 6. Okay, so with 1, so 8 plus 1 is 9, and that will update like this. Okay, so here change is there. Okay, now 7 is done, and I think this is the last. Yeah, so for first cycle, we are doing this process for each vertex. Okay, we are picking the vertex, we are checking the adjacent, and we are updating the distance if we are getting smaller to the previous distance from current vertex. Okay, so in this way, now this is the first cycle. Second cycle, again we will repeat the same process. Now you can see some updation is happened in the first cycle. Now second cycle for one value, so that means we will check the same thing again. So from 0 vertex, now 0, the 0 plus 8 is 8 and 0 plus this is remains same. Okay, so nothing changed. Again you will pick the 1. Okay, so 1 is current distance is 10, so 10 plus 2 is 12, and which is the previous one, so no change is there. If you pick 2, so you can see previously when we picked 2, so there was no update actually. Okay, so here there was no update, but this time now this is updated by the 10 from 5. So from when we are selecting 2, so 10 plus 1. Okay, so now this 3 will become 13, sorry 11, and this 10 plus, okay, this 1 actually will remain same because we are getting higher. So now some updation is happened for 2. Now when we are selecting 3, now 3 is now 11. So 11 plus 3 will become 14 here. So 14 is there. So update is now 4 we are selecting. So you can see 14. And from 4 to 5, you have -1. So 14 minus 1 is 13, which is greater than to the previous, no update. And when you are selecting 5, so you are getting 12 minus 2, 10, which is already there. So no update. 6. So 6, 9, and you can see now update. So 9 minus 4. Okay. So 9 minus 4 is, this was not done. Okay, this was not, yeah. So 9 minus 4 is now 5. So this is now updated, you can see. Okay. So when you are selecting 6, so 1 is updated to 5. And yeah, so 9 minus 1 is now 8. So it will also update by 8. 2 update is happening from the 6. And then 7. So 8 plus 1 is 9. So no change. So you can see each cycle we are updating the value. So in this way, we will repeat this process 8 times. Okay, so how many vertex we have? And after 8 times, you will get the shortest distance from 0 to each node. Okay, so this each repetition is actually figuring out this information, so that in the first iteration, you are getting the shortest distance with one vertex actually limitation. So if from source, you will get the shortest distance with the one edge direction. Okay, if in path one edge is coming to any vertex, so that you will get the shortest distance for that. In the for the second iteration, that means from vertex 0 to any vertex v, if two edges are there, okay, in path, so then you will get the shortest distance for that node. Okay, so each cycle is representing like this. So that means total in path for each vertex. So that means here 8 vertex are there. So total number of edge is possible in the path is maximum 7. Okay, so that means you need to repeat this process at least 7 times. Okay, so because of that we are repeating total number of vertex times. So in when you perform this 8 times, so you will get the shortest distance to the every vertex. So this is the working of the Bellman-Ford algorithm. So now you can see the working here for each vertex. So this second loop is representing the each vertex in the graph, and this vertex we are looking for the adjacent. So for each vertex we are checking all the columns, and if we have the edge from u to v equal to 0, so that means if we have the edge, then we are checking distance of u plus edge distance is less than to the previous distance, then we are updating. Okay, so in this way, after completion of this process, you will get the minimum shortest distance, and here you will get the correct distance for the negative weight also, because here we are again looking the vertex which we have already traversed previously. Okay, so here we are not marking any visited things. You can see we are not maintaining any visited type of data we are traversing, and we are repeating the same vertex again. We are visiting same vertex again and again 8 times. So because of that, this actually handles the negative weights. Okay, so same things you can see in the adjacency list. So for each key, This is the first cycle, and another cycle you can see for each key we are looking the adjacent. So this you can see we are checking the each adjacent of each vertex u, and we are updating the distance if we are getting smaller one. So the implementation is easy, but the complexity is high. So in the exam actually, so this code is actually very easy to remember. So we found that many of the students, if any problems comes with the shortest path, so many of the students actually use this. Generally we not ask the complexity based question in the OPP exam for this. Okay. So implementation wise, the Dijkstra algorithm implementation is difficult compared to this. This is very easy. See, only 3 loop is there and then condition, and you will get the same correct output. Okay. Yeah. So
Sir, I think you already clarified, but still
yes.
asking. So if any question is asked on the shortest path, we can take this Bellman-Ford, and there won't be
So
any complexity constant.
yeah. So generally we not tested the complexity constant in this shortest path problems.
Okay.
Okay. So you can also use this algorithms if you are finding this is easy and if it is taking less time to implement. Yeah, because student actually use this implementation to save the times. Actually, they quickly actually write this implementation instead of Dijkstra algorithm. You can see this is longer. That previous one, yeah, this one. Okay, yeah. So this is Dijkstra algorithm, that Bellman-Ford algorithm, and next implementation is that where it is all pair shortest path. So as we have discussed. So complexity wise, okay, so this Bellman-Ford algorithm, so this one, okay. Yeah. So here, when we are using matrix, we are getting this VQ complexity, okay, because here we, for each vertex, you can see, we are running this number of iteration, then we are also running this nested loop to find out the neighbors. But for the adjacency list, you can see for this loop, inside this loop, we are running only this u in wlist.key. That means for each vertex, we are traversing all adjacent. Okay. So what number of adjacent for suppose 0 vertex, how many edges are there? Okay. For 1, how many edges are there? For 2, how many edges are there? So if you add all these edge, so this will become a number of e. So total edge. Okay. So for each key, if you add all the edge information, that means value information, so this is actually equivalent a total number of edge in the graph. So that means we are repeating this part as a number of e times, and here we are just traversing this repetition for number of vertex times, so key times. So that because of that, this is v and this is total part is a e. So because of that, we are getting complexity of v into e for this next dictionary case. Okay, adjacency list case, v into e. Okay, but in the previous code, you can see we are running all for the vertex. So this is also representing a vertex. This is also representing vertex. This is also representing a number of vertex. So total is become VQ nested. Okay, so this is the third algorithm for shortest path, all pair shortest path. And here this algorithm actually returns a shortest path value for each pair, okay, I and j. And this is a equivalent to if we run Dijkstra or Bellman-Ford on each vertex. Okay, so we have the graph like we have a that n number of vertex. If we run that Dijkstra algorithms on each vertex as a source, so what output we will get is the same output we will get from the float Warsaw algorithm. Okay, so that means we will get the each pair shortest path distance. So the code is again, the code is easy. So here we will have some, yeah, so the understanding is difficult for little bit difficult for this. So we have the graph, okay, So 0, 1, 2, 3, same things. So we will, how many vertex we have? We will repeat the process that time. Okay, so if we have 8 vertex, so 8 times we will repeat this process. Here, conceptually, we maintain the matrix. So what is the original matrix we have? So that we say that W0, or we can say that SP, shortest path distance for 0. And this 0 is represented like, or we can say that not 0, because we have the vertex 0. So this is the initial SP matrix we are maintaining, and this is a adjacency matrix which actually represent the actual graph. Okay, so here 0, 1, 2, 3, 4, 5 to 7, and 0, 1, 2, 3, 4, 5 to 7. Okay, so this is actually a adjacency matrix we are starting from. So this is a original matrix. This is maintaining the information 0 to 8 is 1. Okay, so 0 to 8 is 1, like this. Okay, the original graph information. But after that, we calculate the another matrix from the previous matrix. So this is a original matrix. Now we calculate the information SP0. So that means for this SP0 matrix, for each cell, okay, so we calculate the value for each cell. That means 0, 1, 2, 3 to 7, and 0, 1, 2, 3 to 7. Okay, so for each value, so SP0, that means we are creating a first matrix with SP0. What is the meaning of 0 is here? We are just figuring out that we will consider the direct path from each node, and we will find out the path from 0 vertex. Okay, which one is the minimum? So generally the formula for this is, suppose we are checking the shortest path for 0 matrix. Okay, so SP0 and then I comma j. Okay, and we are calculating the value for this. So we will check in the previous matrix. Okay, what was the previous matrix? So we will check what is the distance SP. Okay, I'm not writing anything in the above. So this is SP. So I comma j direct. Okay, and comma, what is the distance in SP I comma 0. So now if we are considering this 0 plus SP 0 comma j, and among these what is the minimum? So we will select minimum. So that means in the next matrix, when we are considering this 0 and we are calculating the value from I to j. Okay, so I may be anything. So like 1 to 6, we are calculating this 1 to 6. So we will look in the previous matrix what is the direct edge distance. Okay, so if we have direct edge distance from 1 to 6, is there any edge in the graph? We have direct edge from 1 to 6, and what is the distance for this? Okay, and another possibility is, because this is a 0 matrix, so that means we are considering that 0 vertex in between. So we will check this 1 to 0 and then 0 to 6. What is the distance? This path. So direct distance and the path distance from 0. And among these two paths, we will select the minimum one, and we will store that value in this matrix. Okay, so by this formula, we will calculate this information for SP0. Okay, now we will fill this matrix for all place. So total 7 into 7, that means 49 value we will store by this formula. After this, now we will consider the mediator node SP1. Same thing. Okay, so same thing. This is the next matrix. Now we will check the information from the previous matrix. This is SP0. Okay, so we will use the same formula, but this time this will become SP1 and this will become SP0. Okay, so now the mediator node will be like for 1 comma 6. So 1 comma 6, we will check for 1 to 6 direct, and that mediator is 1 to 1 and then 1 to 6, like this. So this 1 will come as a mediator. So if you are getting 2 to 7, so that means 2 to 7 direct, and 2 to 1, then 1 to 6, that's 7. Among these two possibility, which one is the minimum? We will select. So in this way, we will calculate all the metrics. So SP1, SP2, SP3, because we have 7 vertex. Okay, so last level vertex is 7. So we will calculate SP1, then SP2. So that means we will consider this as a mediator node 2, then SP3, and every time we will look from the previous matrix. So sp3, then sp4, and sp5, and sp6, and sp7 for this path. So this will be the last matrix. Okay, and this matrix will actually contain the final result. So basically, we are looking each possibility of the path. Okay, so we are looking direct path, and after that we are looking the mediator one, and we are updating. And every time we are looking to the previous updation. Okay, so we are looking the data from the previous updated value. Now, in the first time we have considered as a 0 mediator. Then when we are considering the 1 mediator, then we are looking the data from the previous data that is already updated. So in this way, now we have checked all possibility of the path. And finally, in this sp7 matrix, we will get the answer, and that will actually represent a shortest path in each pair. So this is actually a matrix. Output is a matrix where you have the 7 row and 7 column for this graph, and you can consider the each that cross value as a shortest path value for the each row and column pair. So in this way, you can see this code. So we are repeating this process this number of times. So 1, 2 column plus 1. Okay, and we are so this graph actually 0. Okay, so in formula actually we are changing some update. So here we are using this k equal to 1. Okay, but in formula you can see when we are calculating this inside the formula, so this will become a 1, and inside this we are changing this k minus 1. So that means this is the previous value. Okay, so you can see sp I comma j k minus 1. This is the direct one. Okay, I to j, and this is I to k minus 1, and then k minus 1 to j. And what value we are taking as a k, so that we are reducing here. So here this, if suppose this k equal to 1, so this will become as a 0. So 0 will consider as a mediator first time. So in this way we are calculating this matrix for each k, and finally we will get the answer that we will return in this matrix. Okay, so in this way you will get this type of matrix. You can see out in the output where you will get this shortest path. So this is the first row, that means 0, 1, 2, 3, 4, 5, 6, 7, and same thing 0, 1, 2, 3, 5, 6, 7. So 0 to 0 means that infinite distance you are getting. So okay, this is 1, 1, 1, 1, 1, infinite, infinite. So this is negative weights, maybe sure.
So basically, in this Floyd-Warshall, it is similar to that Dijkstra and Bellman-Ford. Only thing is, in the earlier two algo, the source node is fixed, but here it is a pair, like any two.
Yeah, this is all pair shortest path algorithm. So actually we are repeating this process that number of vertex times. So it is actually finding out the shortest path between every pair in the final matrix. So you will get this type of matrix, and where each pair is actually representing the shortest path distance. Okay, so 2 to 7 you will get what value you are getting. So this is 1, like this. So you can test this on the small graph. Okay, so you can manually dry run, because this takes lots of time in the manual dry run. So generally we not ask the manual type of question on this type of Floyd-Warshall algorithm, but you should remember this formula. Okay, so what is this formula actually we use to calculate the shortest path? So this is actually important for this algorithm, and because it takes lots of time. So you can see in the every matrix, if you have 7 vertex, that means 49 times you need to apply this formula to calculate each value, and now you need to calculate this 7 times. Okay, so that means 7 into 49 times you need to calculate this information for this graph. So this is very actually time consuming time. So for code wise this is easy, because here you need to just perform 3 nested loop and just apply this, pass this formula. and you will get the all pair shortest distance. And it detect the negative weight cycle if this that 0 to 0 or 1 to 1, if you are getting negative distance on this diagonal value, any in any diagonal value, if you are getting negative value, that means 0 to 0 if you are getting negative value, so that means 0 to 0 if you are getting a negative weight cycle. Because of that you are getting negative value, so that will represent as a negative cycle in the graph. So you can also detect the negative weight cycle in the graph if you are getting the negative value in the diagonal in this matrix at any point. Okay, so the same things, this float parcel also not works correctly on the negative weight cycle, but it handles the negative weights, okay, without negative weight cycle. So that is actually a all pair shortest path. So these are actually a shortest path algorithm. After that we have next topic, spanning tree. So what is the meaning of spanning tree? First, if suppose we have a, so this is a tree actually, okay, as per the name tree, this is a tree. Tree means it not contain any cycle in the graph. Suppose if you have a graph like this, so A, B, and C, and D, okay, and this is the graph originally. So how we can convert this graph into a spanning tree? So spanning tree means this original graph, the nodes of the all nodes of the original graph will remain connected, but that connection will be considered as a tree. That means we will remove all the cycle from the graph. Okay, then that will called as a spanning tree. So if we remove the edge, all edge, that is actually creating a cycle. And after that, after performing these things, our all vertex should remain connected. Okay, then it will become a spanning tree. So for this graph, actually, this consider this is input graph. So what is the possible spanning tree? So you can see A, B, C, and D. Okay, and we have this 4 vertex. Suppose we remove this one, okay, this edge. So now you will get this. Now you can see all vertex are connected. Now there is no cycle. So this is a one spanning tree possible spanning tree. Okay, same you can also consider this as a spanning tree for this. Like suppose if you remove the CD edge from the original graph, so this is also a one possible spanning tree. Same, if you remove this B and C and sorry, C here and D here. Okay, if you remove AC edge, so this is also a one possible spanning tree. So we have many possible spanning tree for any input graph. Now this is, I have just mentioned without any weights. So now suppose if weights are also given on the graph, so like 10, 5, 3, 2, okay. And you can see for the first spanning tree which I am considering here, this one, so that will contain 10, 5, and 3. Okay, second spanning tree will contain 10, 2, 3. Okay, third will contain 10, 2, and 5. So you can see we have the different weights also in the each spanning tree. So all this will consider as a spanning tree. Now we are interested in the minimum cost spanning tree. So cost is here after converting the graph into a spanning tree. If we add all the weights of the spanning tree edges, then that total cost should be minimum in our spanning tree. That tree is actually called as a minimum cost spanning tree. So you can see in the above first spanning tree, we have the total weight 10 plus 5 plus 3, so 18. Okay, now another second graph on the right, 10 plus 2 plus 3, so 10 plus 2, 12, and 3, 15. So this is the 15 one. Okay, and lower one is 10 plus 5 plus 2, total 17. Okay, so now among all the possible of spanning tree, which spanning tree contains the total weight minimum, total cost minimum? That spanning tree called as a minimum cost spanning tree. Okay, so suppose in this graph, if we remove the 10, so let's A and B and C and D. Okay, this one, this one, this one. So this is 5 and this is 2, and lower one is a that 3. So this is the another possible spanning tree. Now we have removed AB, so the total weights you can see 5 to 7 is 10. So this again contains the 10. So among all possible spanning tree, so which one contains the minimum total cost? That called as a minimum cost spanning tree. Okay, so you can see here. So here 4 possible spanning tree are there for this graph. If we remove one as okay from every graph, so we are getting 4 different spanning tree, and among these 4 we are getting the 10 cost on this spanning tree. So this is called as a minimum cost spanning tree, MCST, sometimes MST. Okay, so this is the minimum cost spanning tree, and how we can figure how we can find this minimum cost spanning tree from the graph. Okay, this is our task. So we have 2 algorithms for this, Prim's algorithm and Kruskal algorithms. And the some common example for this is, suppose you want to connect. So like if you want to spread the fiber optical cable to connect some cities, and you want to use the minimum length of the cable to connect all the cities by the fiber optical cable. Okay, so here you can consider that the all possible distance, suppose this is the all 4, these are representing as a city B, C, D. Okay, and now you want to connect all this city by a minimum length fiber cable. Okay, so now the distance from each like this are given to you. Okay, so like this, these are the all possible. So this is 10, this is 1, this is 5, this is 4, this is 6, this is 7, like this. Okay, so A to D distance, direct distance is given like this, and you want to just connect all the cities by the minimum length of the fiber. So how you can figuring out this if this type of information is given? That means the graph is given, you need to figuring out the spanning tree which connect all the vertex with the minimum total cost. So you will figure out that in this graph you can see. So if we connect this AC and or this B, D and this one, right? So you will connect all 3, all 4 actually, A to C, D and B, all are connected, and the total cost is 1 plus 5 plus 4 is 10. This is the minimum cost spanning tree. Okay, so this type of many real-time problems can be created on this topics, the minimum cost spanning tree, which is actually a one important application. Yeah, so we have 2 algorithms for this. One is Prim's algorithm and another is Kruskal algorithms. So first I'll discuss this Kruskal algorithm, and this is very easy to apply the dry run on the Kruskal algorithms on the graph. If any graph is given, you can easily apply this Kruskal algorithm, okay, and to calculate the spanning tree cost. So the purpose is purpose of the both algorithms are same. That means you will get the correct output by the same both algorithms, same output. Okay. Suppose any graph is given. So any graph is, yeah, this is given. So how actually that Kruskal works? So how many edge we have? So Kruskal actually works on the edges. So Kruskal actually filter out all the edges of the graph. So how many edge we have here? So we will note down this 6. 1, 2, 3, 4, 5, 6. Correct. Now Kruskal collect the edges, and Kruskal sort the edges based on their weights in increasing order. So that means we will pick the edge in the increasing order by that distance in between. Okay, so which one is the smallest distance edge? So 1, 2, 3. So I'm noting down this 1, 2, 3. Okay, have the distance 6. Okay, next higher is 2 to 4. Okay, so 2 to 4 is 8. Next highest is that 0 to 1. This is 10. Next one is 18. Yeah. So 18 is 0 to 3 is 18. Next one is 1 to 2, which is 20. And next one is that 3 to 4, 70. Okay, so now this is the collection of edge, and now we have arranged these edge in increasing order of their weights. Now we will just take the all vertex like this, 0 and 1, then 2, then 3, and then 4. Okay, now we will pick the edge one by one from the top starting point. Okay, which one has the minimum? So 1, 3, we will pick this edge and we will check if this edge is creating a cycle or not. Initially we are starting with the graph where the each vertex is actually disconnected to the other vertex. Okay, that means here each vertex actually a disconnected, that means separate component. Okay, now we will connected these separate component by the edge, and if any edge is creating a cycle, then we will not consider that edge. Okay, we will ignore this. If edge is not creating a cycle, then we will consider it. So you can see first we are picking 1 to 3, and this the weight edge is 6. So 1 to 3 we will connect. Okay, so now these two disconnected component now connected by this edge with 6. Okay, and mark this, and it is not creating any cycle. Okay, now we will pick 2 to 4. 2 to 4 is 8. So you can see we are, when we are picking this 8, it is also not creating any cycle in the graph. So this will also consider. Now 0 to 1. So 0 to 1, when we are picking this, so this is 10, it is also not creating any cycle. Okay, so we will also consider this. 0 to 3 is 18. So 0 to 3, you can see if we are considering this 0 to 3, it will create a cycle. Okay, so that means it will not remain a tree if we connect this. So then we will not consider this. Okay, now 1 to 2. So 1 to 2 is 20. So 1 to 2 is 20. This one. Now it is not creating any cycle. And 3 to 4, when we connect this, now it will become a cycle. So we will not consider this. So by this process, you are getting a spanning tree with minimum cost, total cost. So the total cost is now 6 plus 8 plus 10 plus 20. This is now 44 for this. Okay, so this spanning tree is now a minimum cost spanning tree. So this is the working for Kruskal algorithm. Okay, so you will get the answer for this. So now Prims, I'm moving to the Kruskal first. So how Kruskal actually works? So Kruskal use this component information initially. So you can see we are maintaining this edge component and this tree edge. Okay, T means tree edge. This 3 data structure for this. Initially, W list. So what we are doing, weight as first value in the top. Okay, so what we are doing, we are changing the information. So for edge information, so W list, what we are passing. Okay, we are getting the adjacency list, and from adjacency list for each V comma D. Okay, so for V comma D and for each U. Okay, so for V comma D in W list U, yeah, U is the key. Okay, so we are removing all the edge. Okay, and we are creating a list of edges, and we are fetching all the edge information from the adjacency list, and we are maintaining the weight as a first value in the tuple. Okay, because we want to sort this list based on the first value in the sorting order. So because of that, we are removing fetching this information, edge information from adjacency list, and we are containing this D means weight, and then U and V is the vertex which are connecting by the edge. So that information we are fetching in the tuple, and now we are getting this edge list. And after that, you can see component of U. Initially, we are also maintaining this component of U equal to U. So that means initially each vertex actually a separate component. So here, that means what is the component value for this is 0, this is 1, this is 2, this is 4, this is 5. So the component value for each vertex is the same. Okay, so 3 and 6 initially. So that means initially each vertex as a separate component. Now you can see we are sorting this list. So this edge dot sort equal to will return a list where the edge will be sorted into the increasing order of the weights. And now we are traversing each edge and we are checking if component of u does not equal to component of v. So what is this? So here in the each edge, so what we are doing, we are maintaining the same informations for this graph. Let me explain this also. So again, the edge vertex, so what is the minimum is 1 to 2, 6, and next is not 6. Okay, so yeah, 5 to 6. 5 to 6 is 5, and okay, 6, and we have 3. Okay, so 0 to 1 is now 10, and 4 to 5 is 10, and 4 to at 6 is again 10, and now 18. So 0 to 2 is 18, and then 1 to 4 is 20, and 2 to 3 is 70. Okay, so this is the edge information we have. Now this is the component information I have stored. Okay, so what we are doing, we are picking the edge from the first, and we are checking at the time of connection. Okay, so when we are connecting this 5 and 6 in the original graph, so I will mark this in the main graph. Okay, so yes, okay, so when we are connecting 5 and 6, that means this edge. Okay, this is 5 to 6. Now we are checking this, what is the component value of 5, and what is the component value of at this time 6. If the component value is different, then we will do the process. If component value is same, then we will not connect the edge. Okay, so that if component value is same, that means both are representing from the same component. Okay, and if component value is different, that means both vertex are represent to the different component, then we will connect the edge. So this component actually we are maintaining for to detect the cycle. So you can see in the first step, 5 and 6, the component of 5 is 5, 6 is 6, both are different, then we will connect this edge. After connecting this edge, now we will give the same component value for the each vertex. So that we are doing from the code. So now you can see in this, if this component is not equal, then what we are doing, we are appending this edge into the tree edge, and now we are checking what is the component value for u. This is C, and we are updating this component to the each adjacent of this of the current component. So here what we will do, we will check 5. Okay, so initially we have this type of graph, so let me make separate. So like this 0, 1, 4, 5, and 6, and this is 2, this is 3. Okay, so initially each component is separate. So what we are doing, we are connecting this. Now this become a one component. Okay, after connecting this edge 5 and 6, this is now become a one component. So now we will update the component value for this all vertex. So the component for 5 will remain 5, and we will also update the component for 6 is 5. Okay, so now this is representing that the component for 5 and 6 is 5. So that means both are that these vertex are coming to the same component. Now next time when we are adding same thing 1 to 2, so same things 1 to 2. Now component of 1 is 1 and component 2 is 2. Both are different, so we will connect this. But after connecting this, we will make the component same. So that component 1 will remain 1, and 2 will component 1 will become also same 1. Okay. So now next is 4 to 5. So 4 to 5, you can see the component of for 4 is 4, 5 is 5. Both are different, so we will add this. So 4 to 5 we will add, but this time, so you can see what the component value for 4 is 4. So this is 4. Now we will update all the components. So what are the component which are connected to this 5? Okay, so this will also update by 4, and this will also update by 4 like this. Okay, so we will traverse all the vertex Okay, and if any vertex have the component 5, we will update by the 4. So now this part is representing to the same component value 4. And next is
So
4.
now 4 and 6 can't be connected, right?
Sorry, 4 and
4 and 6 will not be connected now.
so next time, suppose if you we have done this 1 0 1 we have done okay, so 0 1 we have sorry escape. So that means when we connect this 0 1, so this will connect it, and now the component value will be updated like this 0 0 0 for all. And when we are updating 4 to 5, now we have done, and when we are updating 4 to 6, okay, so you can see what is the component value for 4 is 4, and what is the component value for 6 is same 4. And this is actually representing information that we are trying to connect the edge where the 4 and 5 6 both are related to the same component. That means if we connect this edge, it will create a cycle. So because of that, we mentioned this condition at the top. You can see here this one: if component of u does not equal to component of v, then we will do the connect the edge, otherwise we will ignore. Okay, there is no else condition for this. So if component value for both are same, so we will ignore the process. Okay, so this 4 to 6 actually will be ignored, because here the component for both these 4 and 6 are coming from the same component, which is already connected. So this will be ignored. So 0 to 2, you can again see. So the component of 0 is 0 and 2 is also 0. Again, this will also create a cycle, will not consider. And 1 to 4, so one component is 0 and component for 4 is 4. So both components different. So now we will update this. Okay, but after adding this, the component of 1 actually, which is 0, will be assigned to each component for another part. So 4 5 6 all will updated by this 1. Okay, next updated value 1. So now all are coming into the same category. Not 1, sorry, 0 0. Yeah, 0. Okay, because the component of 1 was 0, so that will be assigned to the each for 4 5 6. Okay, now this 4 connected. Now 2 and 3, now you can see 2 is 0 and 3 is 3. Okay, now this 4 connected. Now 2 and 3, now you can see 2 is 0 and 3 is 3, still not connected. So when we connect this 2 and 3, so the 2 parent is 0 and that will be also be assigned to 3 parent, sorry, component 0. So now you can see all are connected. This is connected. So now you can see all vertex have the same component 0 and all are connected. So this will consider as a minimum cost spanning tree. So in this way, this algorithm is working with this component. So you can see the code now, and this code is working in the same way. So for each edge, we are checking this component of u does not equal to component of v. This condition is actually giving this information that our u comma v edge is not creating a cycle. This is true. Okay, so then if this is true, then we will enter inside this. We will add this edge into the tree edge. We will find out the component of u, and then we will update this component for the each vertex of the that w list key. Okay, so we will traverse all the keys and we will check if the component of v w equal to c, and then we will update to the new component value for this. Okay, so in this way, you can maintain this Kruskal algorithm, and you will get the tree edges in the final answer. So you can return this TE, and this is representing a tree edges. And you can also maintain the total cost. You can maintain one variable for the cost. So just add that cost value when you are entering inside this. Okay, and you can return directly the total cost. So this is one algorithm, Kruskal algorithms, and another we have the Prim's algorithms. And Prim's algorithm is very similar to the Dijkstra algorithms, only one small modification. Okay, so how Prim's algorithm is actually works? So let me explain. Uh, so I'm taking this graph. Okay, so Prim's algorithm actually works similarly to the Dijkstra algorithm. Okay, so that actually start with the same things with zero information. You can, if you are starting from this vertex, suppose you can start from any vertex in this. Okay, there is no source or destination things. But if you are starting from zero, so initialize with zero and remaining are infinite. Okay, so now this time we will start from this and we will check the adjacent. So 0 to 1 and 0 to 3. Now in this algorithm, we will not add the previous distance. Okay, what is the current distance of the node? We will not add, we will only look the current edge distance. Okay, if this edge is connecting, when we are considering this edge, and what is the next this value, updated value. Okay, so here you can see in the first time 0 to 1, 10, and this 10 is smaller than this infinite value. So we will update this by 10. Okay, and same things from 0 to 3. So this is 18. 18 will be updated by here. Okay, so 18. Now we will pick the smallest distance. So this is the, this we will pick, select the node. And when we are picking this vertex, we will consider this as a tree edge. So now this will be selected as a tree edge. And this is okay. So now when we are picking from this one, so now we will check 1 to 3. So now this is 6. Now we will not add this 10. Okay, so we will only consider the edge. So this is 6 and previous is 18. So we will update this 6. Okay, and we will also maintain this. You can also maintain this information where from you are getting this 6. So based on that, you can select the edge later. So this is now select updated, and same 1 to 2 is 20. So this is 20, which is smaller than, so 20. Now this is the next updation. So which is the, now next is 26 and infinite. So you will select this 3. Okay, and where from you are getting this 6? Here. Okay, so this edge will be selected. And now when you are picking this 3, so you are moving to this unvisited vertex 3 to 4, 70. Okay, so this will be updated 70. So now this is updated. So 70, next time which node you will pick? This 2. Okay, this one. And when you are picking this 2, so where from you are getting this 20? From 1. Okay, so this edge will be selected. Okay, now from 20, this 2 vertex, you have the S8. Okay, and previous distance is 70. So this 8 is smaller than, so this 8 will be considered. Okay, so now 8. Now only one node is remaining. So 8, where from you are getting this 8? This edge from this parent. Okay, so finally you can see you are getting this. Okay, so 0, 1, 2, and 3, and 4. So 0 to this, and this one, and this one, and this one. Okay, so this 10, this 6, and this 20, and this 8. So this is the spanning tree for this. Okay, so this algorithm is very similar to the sim-dashed algorithm, but we are not only adding the previous distance at that every time when we are updating the distance. Okay, so you can implement this algorithms. So you can see the implementation which is given. So this is Prim's W list. So same things you can see. We are maintaining the infinite. Okay, visited distance tree as we are maintaining same. And initially we are maintaining false and infinite for the visited and distance. And then for source, if you are starting from 0, then consider as true. And for distance, you are calculating this V to D. Okay, okay, yeah. So this is the first step here we are doing. We are checking the adjacent of this 0, and we are updating the distance directly by this. Okay, so distance of V by D directly, because this is the first step. And after that, we will use the loop, repeat the loop process, and same things you can do. Min distance we are setting to infinite initially. This is the, and next v equal to none. But then we will check the min distance again by this loop. So for we will traverse all the key, and for all the keys, and we'll repeat this process. And for u vertex, okay, so for each key we will check the adjacent vertex, and we will check if visited of u. That means we if this is visited, U is visited, and the V actually is not visited. Okay, so we are actually in this way we are selecting this U vertex initially. So this we are reading the key correctly. So this key will traverse 0 key first. So 0. So in this way, now we will check if U is visited and the adjacent, the edge which is connected from that U. Okay, so this is actually V. So if that is not visited and the distance is less than to the minimum distance. So what is the previous minimum distance is infinite. If you are getting this information, you are updating this main dist by D, and next V equal to V, and next E equal to this edge, and this is the vertex. Because some is some implementation is different, but the process is similar. Okay, so we will repeat this process again and again, and every time we will get this information, the minimum vertex node we will select, and we will do the same process. But you can see here how we are updating this distance. So D, if you are getting D is less than to the previous minimum distance, then you are updating this. Okay, so you can apply one dry run on this. Implementation is let me see, I have another implementation was there. Okay. So this is the another version implementation. You can see the previous is a little bit confusing implementation. So here you can see we are doing the same way. So the source distance where from we are starting 0. After that, we are repeating this process for n total number of vertex minus n times, and then you can see we are finding out the minimum distance in the same way as the Dijkstra algorithm. Okay, and then we are finding out the vertex with the minimum distance, the number of vertex which have the minimum distance, and among all these vertex we are figuring out the minimum label vertex. Then we are selecting, then we are marking that vertex as it true, and after that you can see we are checking all adjacent of that vertex. If that adjacent is not visited, then we are checking if distance D is less than to the distance of V. You can see here we are not adding the previous distance. Okay, so we are only looking the current edge distance D is less than to the previous distance V. Then we will update this neighbor distance. We will update, and we will update this NBR to V is next V. So this is for actually similar to the parent, where from we are getting the edge, and distance we are updating with the current distance. Okay, so this implementation is very similar to the same Dijkstra algorithm. So previous one is little bit confusing, so you can consider this. So here you will get this information like 0, that is no source, but for 1 you are considering the edge from 0. So 0 to 1. So this NBR is representing a parent information where you are coming from. So that edge you will consider. So for 2 vertex you are coming from 1 vertex. Okay, so for 3 you are coming from 1 vertex. For 4 you are coming from 2 vertex. So in the spanning tree. So this is also representing a spanning tree information. Okay, so in this way you can implement this, but same things. So in this implementation, the similar type of question is asked, like the order of visited node. So what is the possible order? And same thing, most of the time that minimum spanning cost actually asked. If any graph is given, what is the minimum cost spanning tree? Okay, so yeah, these are the topics. We have the Kruskal algorithm we have already done. Otherwise purpose is same. If sometimes if the implementation sub question is comes like from the programming side, so you can follow any approach. So you can pick Kruskal algorithm if you find that easy. Okay, so because the both algorithm will return the same output. Okay, so these are the topics from Week-5 actually we have. So if you have any query in this, you can ask. So any query in this? So if right now, if you don't have any query, so after quiz you can just watch the video of the professor and then come with the query, and then we will discuss. Okay, if you have any query in the coming session. Okay, any question, anyone?
No, sir.
Okay. Okay, so just prepare for the quiz one first, then after that we will discuss this in the coming week also. Okay, then if there is no query, then we can close the session. Yeah, thanks everyone. Good night.